Okay, so in today's class, we will learn a few more performance analysis metrics, and post that, we will start with shared memory programming, shared memory multi-threaded programming using p-threads. So we've seen so far execution time, the time taken for executing a particular application. Latency is time taken to do one task. It could be one program, one instruction. Throughput is number of jobs which are completed per unit time. It could be in terms of memory, it could be in terms of number of instructions executed. It, throughput can be in terms of per second or per cycle. How do we calculate speed up? Is we divide the execution time by one program by another. That is the ratio of their speeds of, let's say, P1 and P2 is the speed up that you have achieved. Cost is calculated by number of processing units involved by into the time taken for completing the execution per processor. So basically, time complexity of a problem into number of processors you've employed.
Ma'am, one query here. So latency, on latency part, execution
Yes.
anyway, we understood the from the
Hmm.
parallel section of the program to the end. It is a execution time for the parallel.
Hmm.
But latency, we are also considering the complete one program to when it is completing time, taking time, whatever time it is. We are
Hmm.
considering latency. But
Hmm.
are are we not? But that shouldn't be considered into the execution time overall for the entire program, because the program may have sequential plus the parallel sections, right? And
Yeah, yeah. So,
latency can be like when, let's say, when we are submitting the program, then the after submission, the it has to be divided into the instructions, and then the time taken to the division, then assigning the processes, then starting the execution. So that time can't be considered latency.
so latency can be defined in different ways. It is
Mm,
basically the
yeah.
time required to complete a job. Okay, that job can be an application. The job can be completing execution of one instruction
Mm,
or any other task. So the
okay.
total time or total delay which is involved in doing a task is latency.
Okay.
Okay?
So, but at least so any program we are submitting, that
So
will definitely take some time. So how are we considering that as a latency? That's the thing I'm trying to understand.
latency is, so why it is considered latency is latency, and if you now consider, let's say, execution time and latency, then
Mm,
of a program both will be same values of a program. Okay, because the total time or delay taken for completing a program. Okay,
mm,
but
I think what
yeah.
Ravi is mentioning is that anyways, whenever we are running any computational task, right, whether it's
Mhm,
a thread or maybe it's the entire program, anyways, it will
mhm.
take some time to execute, right? I mean, it might take 5 seconds, it might take 1 second, it might take an hour. So how are we considering that as a latency? Because anyways, some amount of time will anyways be taken, right, to complete that task.
Yeah, so latency anyway, the definition of latency is delay or time it takes to complete a task.
okay. Let me put in this way. My
Yeah,
understanding
yeah.
is,
I
let's
think
say,
I'm still, yeah, it is
yeah,
okay.
T0. Let's say at T0 we submitted the program. Okay,
Mhm,
and
mhm,
in between whatever happened, T1 is the actual time when the program started the execution, and T2 it took to complete. Now, what you just explained is from T0 to T2, it is overall considered as a latency, correct?
Yes, yes.
I'm still not able to understand, but okay, I'm leaving that. I'll try to figure out an online. Yeah, thanks. Because generally latency, so in case of example of network, I'll give you the network example. So network, in network we consider latency where we got the response time slow response time or drops or something, right? But
Yeah.
ideally we know that this is the time anyway it will take, right? If it is a within the same network, then one with less than 5 ms, there will be the time which is expected. More than that is considered as a latency. Similarly, like that as
Okay.
in overall also. But in case of like in the program execution as well, we know that any program will take x amount of time, that is for sure, right? So general understanding of the latency is that okay, this is the expected time, but over than that, if it is taking more, that is something we consider as a latency, because it might be stuck somewhere, it might be doing something, right? Just like I just mentioned, when we are submitting the program, so after submission it will go to the cache, it will like memory, then it will breaken down to the instruction, then it will the instruction will be assigned some processor, and then the processor will start. So in between whatever happened from submitting to the actual start, that is something we can my understanding that that can be considered latency. But if we are considering complete program execution, that's something I'm trying to figure out. So
Okay.
okay.
Latency includes waiting time. That can be,
Mhm,
that can include network transmissions or queuing.
mhm,
Okay.
mhm,
But
mhm.
when we talk about execution time, we basically trying to measure the CPU time, which includes, we also, okay, which may also include idle time.
Right.
Okay.
Yeah.
So, so purpose of latency is that you focus mostly on delays, while execution time we focus mostly on the processing time for the problem, right?
That the execution,
So,
that is we are considering only for the parallel section, not for the sequential, right?
hmm, uh, that it yes, the parallel section. If we focus, yes, it will be only for the parallel section.
So, ma'am, one more question here, right? So you're saying that execution time is obviously for the entire set of processes, right? One single program.
Hmm, hmm.
But when I talk about latency, are you saying that it is for a single process, or that is also for the entire program only?
So, it will depend on which latency you're trying to calculate. If you want to calculate it for one program, if you want to calculate for the whole program, if you want to calculate it for one particular instruction, it is the delay that taken to complete that task.
So,
Total
ma'am,
delay.
if it's a single process based program, right? A single unit is there. In that case, the execution time and latency will be same, right? If that is the case, how will we
Yes,
differentiate? That
yes,
is okay.
yes.
All right. Yeah.
Effectively, what is the exact difference between execution time and latency in a, in simple words?
Okay. So now, yeah. So see, both execution time and latency, can like be similar, or they may appear to be similar if you're trying to calculate it for a particular, you know, uh, thing like execution of a program. Okay. So uh, now, as I mentioned, in execution time, we try to focus on processing time, whereas latency focuses on using the total time, including waiting and transmission time, the delays that happen. Okay. uh, in case if execution time and latency are similar, the what we consider in latency is, or the focus is on how much delay that happens. That is the waiting time that happens. Okay. So, um, um, I, so an example could be, let's say, uh, we have, okay, so the if we let's say we have a web server and it is trying to process some requests, and it needs around 10 milliseconds of CPU time to execute. Okay, so what happens is the server receives requests and it will send some response back. So the execution time would be approximately 10 milliseconds because that's the time the server, the processing time for the server. But the latency might can include the network transmission time, that is how much time you take to receive the request and how much time you take to send the response. It will also include the server processing time, the CPU time, and if there
Okay,
is
so
any other
so
additional
latency,
waiting
we are
time.
considering the overall time, including
uh,
latency plus execution.
yes, yes, yes.
Okay, got it.
Yeah.
Okay.
So total time could be maybe around 20 milliseconds, including all these
Mm.
three, four tasks. Whereas execution time, we can say it was only 10 milliseconds on the server.
Okay.
It's clear?
Okay. Okay. So more often than not, latency is going to be greater than execution time. More
Yes,
often than
yes.
not.
Yeah, more of, yeah, yeah.
Yeah. That is nice.
Yes. So what is a cost optimal system? We discussed this last time.
Any any process which is, I mean, taking time less than the sequential program execution, that will be cost optimal. I mean, parallel program execution will should be less than the sequential program execution.
Multiplication of serial execution time by the processor.
No, multiplication of
Serial
execution time
execution
in
time.
parallel. Multiplication of execution time in parallel into number of processors should be
Okay.
less than or equal to the time taken for executing it in serial.
Okay. Yeah.
Okay, so I think last time we saw an example which is O of which we could mm, calculate using O of n serially, but with parallel execution with n processors, we could execute it in O of log n, but the cost became the number of processors, that is p into log n. So p
Yes.
into log n or n log n is greater than O of n. Hence, the cost became greater for parallel execution compared to serial, and hence that solution was not cost optimal. Okay.
Okay.
So yeah, and the efficiency is the fraction of time for which the processing element is usefully employed, and we calculate, how do we calculate
Is say speed up by P.
it? Yes, so it's speed up by number of processors involved,
Yes.
and in so and its value is usually between
Uh, 0 to 1.
0 1.
0 to 1. Yeah, and 1 is the ideal system. And practically achieving 1 is not possible,
Yes.
considering, yeah, multiple overheads. So uh, sometimes using fewer processes can improve the performance of parallel systems, and uh, and so the same problem that we discussed last time, we can now see another version of solving that problem and see if we can make the problem, the solution, cost optimal. So, uh, so last in the last class we used n processors. So here we will use n by p processors, and we will try to divide the numbers also by a factor of n by p. What is happening here? is we had n processes last time to do the addition. What are we doing now? We are divided the we have taken 16 processes and divided the sorry, we have taken for 16 elements 4 processes and we divided the elements between these 4 processes. So here what happened is now each processor is responsible for doing the addition, right? So here the first processor is doing the addition of 0 and 1. The second processor is doing the addition of 2 and 3, right? So it is communicating between each other and doing the addition. So in the next step, 4 and 5 and 7 and 6. Next step, 8 and 9 and 10 and 11 and so on. So in the end, the final results, the first processor is able to compute the sum of all the elements, all the 16 elements. Okay. So what do you think is the now the time complexity?
Ma'am, can you please explain again how the problem was divided into 4 processes? How that division happened?
So
We have numbers from 0 to 15. So 16 numbers are there. How they are broken into 4 parts?
so we 16 numbers are there. Each processor gets 4 elements. Okay. And
Hmm.
each processor is supposed to add 2 elements, one of its own and the other one from the neighbor.
Does
Okay.
that mean each process is allocated with column?
Yeah. The column is associated with each process.
Okay. Okay, I see. I see. So 0 is basically process 0, 1 is process 1, 2 is
Yeah.
process 2,
So these,
and
yeah,
so on.
circles are processors. Yeah, circles are processors, and the
Okay.
elements are shown above the processors.
Oh, okay. Yeah.
Ma'am, in this case, the other, I think processor 1 and processor 3, they are
Hmm.
being idle, right, after some time.
Yeah.
In such,
That happens in yeah, in such problems that happens. They remain idle. And only one at the towards the end, only one processor is doing some useful work. Okay, so in this problem, we are doing adding n numbers on p processing elements, and we have chosen p, which is less than n, and n and p are both powers of 2. So here p each p processor is assigned n by p virtual processors, and what we do is the first log p of the log n steps of the original algorithm are stimulated using n by p log p steps because we divided the elements into n by p. Then the remaining steps will be log n minus log p steps, which may not require any communication. That is here, after this step 4, there is no communication required because the processor itself has all the elements. So the overall execution time here of the system becomes n by p log p. Okay, and hence the cost becomes when we multiply theta of n by p into uh, log p into p, the cost becomes theta n log p, but it is still higher than theta of n. Okay, so the system is still not cost optimal, even if we use this approach. Because although we are dividing the elements amongst processes, the, there is communication involved and the number of steps increase. Is there any other way you think we can make it solve it cost optimally? Okay, so what if we, when we divide the elements, each processor is not so much supposed to communicate with the other and do the addition. What if it is supposed to do the addition by itself for all the elements that it has been given? Okay, and then it can communicate in the next step the elements each one of has and then do the addition, total addition. So we are able to finish this task in 4 steps, isn't it?
But ma'am, this might not hold true for every computation, right? Addition is separate. What about we had something which follows BODMAS kind of a rule, right? Then we can't go with this approach because there's a dependency on other processor to provide the output.
What kind of approach? What did you say? Broad? Uh, what did you say? Sorry, I missed it.
BODMAS. BOD.
Okay.
So basically a collection of brackets, then divisions, multiplications, the equation kind of a thing. Because in that case, we need outputs from other things in between, right?
Okay. Yeah. So yes, this may not work for all the solutions. I agree. But for this particular problem, just decreasing the communication between processors and trying to do tasks per processor can help you to make the solution cost optimal. Because we are finishing this in log p time compared to the same solution by n by p, but if communication is involved, can increase the number of steps. Is it clear? So the total time is dividing this amongst n by p and the log p time it gets complete. The completion of the summation of
Ma'am,
all the elements. Yeah.
can you please repeat once again this algorithm? Unable to understand properly.
Okay. So yeah. So okay. So now in the last class we had seen that if we have n elements and we use n is equal to p processors, okay, and each processor is supposed to do addition, we could solve this problem by n, with log n steps, okay. But because we were using the number of processors equivalent to number of elements, what happened was the solution was not cost optimal. So the cost of I'll use the pointer. So the cost was still the number of steps, although were log n, because we had to multiply with n number of processors. The cost was n log n, which was greater than O of n. Now, how can we make this solution cost optimal? Okay. First step is what if we tried is what if we do not have n processors, but we decrease the number of processors that we use to solve this problem. From n, we decided to use n by p processors. Okay, so p processors, which is p is very less than n. So here for n is equal to 16, we used a P which is 4. Okay. Now with 4 processors, each of them here the circular brackets are processors. This is P0, P1, okay, P2, and so on. Now total N is divided amongst all 4 processors. Each one has now N by P, so 16 by P is 4. So each processor gets 4 elements. Now, if we try to solve this problem, we are looking at solving this problem with 2 approaches. In the first approach, what we are doing, we are each processor is communicating with its neighbor and doing the summation of 2 elements at a time. So first step, this plus this, it stores the result, and this processor, second processor, is adding its element with element of process 3. Next step, the next row elements are added. Then the next row elements are added. Then the next row elements are added. Now, in step, this becomes the first, iteration. In the next iteration, what it's doing is now processor 1 and processor 3 remain idle. Processor 0 and processor 2 communicate each element of each row and do the addition. Okay. So here the first 2 elements, then next 2, then next 2, and next 2. That's how the second iteration happens. In the third iteration, now we are adding, so the processor 0 has all the elements. So now it is adding 2 elements at a time. Again, the first and second, then the next 2, then the next 2. So, and finally, it gets the sum. Okay. If we use this approach of communicating one element at a time and doing the addition, so this approach, the execution time becomes, since we have N by P processors, the what happens in the first log P steps, we simulate using log of N by P, and the remaining steps, there is log N minus log P steps, is the last, basically the last step that we saw in this example. We do not require communication because all the elements are on the same processor. So the overall execution time becomes, we divide the elements into N by P, and each processor performs log P steps. N by P, log P. So N by P, log P into number of processors is again P. When we multiply this, we get the cost theta of N log P. But theta of N log P is still higher than theta of N. So hence, the solution is still not cost optimal. So dividing the number of data points into the number of processors, we have not still got a cost optimal solution, because here we are communicating at every step with the next processor, getting its element and doing the addition. Okay. How can we make this solution cost optimal? As we have seen, the biggest overhead here is communication amongst processors for each element. If we develop a solution which will involve, again dividing the elements amongst each processor. Now each processor is supposed to do the summation of all the elements in the first step that it has. Okay. And in the next step, it communicates its value to the next processor. In the third step, it sends its value. Two processors remain idle and 2 processors active, and they share the values. And in the final step, you are able to solve this problem and get the sum. So this way, in we are able to get p partial sums on p processing elements in theta of log p. Okay, and each processing element is adding its n by p log numbers in n by p time. So what happens is each processing element calculates adds its n by p in elements by in theta of n by p, and the partial sums on p processing elements is added in theta of log p. So the total time becomes n by p plus theta of log p.
So, ma'am, if I understand correctly, so the earlier example where every computation was first being done between the processor, then they were adding the rest of the elements. Uh, can we consider that as a what do you say? Um, uh, I mean, this particular approach can be considered as a coarse-grained parallelism, or earlier was the fine-grained parallelism. Can we consider that? Like, what we are doing right now is, in earlier case, the processes are communicating to execute, right? So that in that scenario, the communication overhead is more than the execution time. And in this second scenario, what I'm understanding is the execution time is more than the communication overhead, because right now first each processor is first executing and then it is communicating. In that earlier case, the each processor were communicating first and then doing the execution.
Yes, yes. I
Is
think
that understand
you
correct?
are. Yeah, we can say that these are two approaches. The first one was a fine-grained approach
uh,
where we were breaking down tasks into smaller tasks
mhm, mhm.
and which were being done concurrently. But there was high synchronization. That is, or communication involved.
Yes, yes,
The
yes.
first one.
So
Whereas in
overall,
third,
we are seeing the overall when we are, because we are seeing the two portion of the granularity, correct?
yes, yes, yes.
Okay, thank
So
you.
here the task is larger, that is adding more elements, but there is less frequent communication involved here. The second approach. So we can call them fine grained and coarse grained approaches. So now, since the mm, time becomes n by p plus log p, and if when you multiply the p to this value, what happens is n by p into p will n will remain, and p log p it will be, so n plus p log p. Now p log p, if as long as the p log p value is very less, this is quite equivalent to theta of n, right? So this, as long as p log p is equivalent to n or less than n, this value becomes equivalent to theta of n, and hence this solution becomes cost optimal. Is it clear now? Or anyone still has doubts? Okay. So, having said that, we cannot make all the non-cost optimal systems cost optimal by just scaling down the number of processing elements. It's not possible. Okay. But this is one example where we could do it, but not every solution can be made cost optimal. Okay. So another metric is total parallel overhead. Here, the total time that we spent in solving a problem over all processing elements is P into TP, which is the cost, and TS is the time we spent performing some useful work. That is the time taken for solving the problem serially. So the overhead is PTP minus TS, and this is how we can get the total parallel overhead of solving a problem.
And one
Now,
question here.
yeah,
So this PTP is for parallel processing.
Yeah. Uh, I think we dropped.
Can you hear me now?
Yeah, yeah, yeah.
I'm saying this PTP is for parallel processing and this TS is for sequential processing, right?
Yes.
And we are considering that only a small portion of the program is sequential because we can't make everything as parallelized program, right?
Hmm. So
Ma'am,
basically,
this one,
PTP.
can you explain one more time?
Okay. So, so PTP is the total time taken for solving the problem parallelly on all the processors minus what exactly we need from this solution is TL, the serial, right? Sorry. So, if we consider the previous example, the solving the problem is using the n processors will give us O of log n, whereas doing it serially we got O of n, right? We could do it in theta of 1 or O of n. So the extra time that we end up spending, or the extra the extra execution time, or that we end up spending because of using more processors, which includes, the synchronization task, the communication time required, or whatever extra we end up spending is the overhead, the total parallel overhead, which is
Okay, got it. I mean, the
additional
ex.
cost of,
Okay.
yeah, additional cost associated with parallelizing any program. It could
Mhm.
be synchronization, it could be
So,
communication, it could
is
be
it
thread creation.
here we are finding that in terms of overhead, in terms of time, right? The extra time that
Yeah,
is spending in synchronization
yes,
communication,
yes,
right? Okay.
yeah,
Okay.
yeah, yeah. Okay. So, yeah, did we discuss Amdahl's law before? I'm not very sure. Uh,
Not here. I
No,
mean,
not till
in
now.
not,
No,
not
in
yet.
not
some
Okay,
other
in
okay,
this
subject we
class.
okay,
also gone through.
okay, okay. So,
Red,
yeah,
ma'am,
so if,
sorry,
yeah,
sorry to interrupt. There is one word used as part of earlier slides,
mhm,
asymptotically. Even earlier, I think there was a mention of word called asymptotic.
yeah.
What? Yeah, just hold here. The cost is theta n log p, which is asymptotically higher than theta of n cost of adding n number sequentially. What does that asymptotically word signify?
So, yeah, so, the asymptotic analysis, which is getting the upper bound, like big O, big omega, lower bound, theta, which is the exact bound on complexity, right? Okay. So, with asymptotic analysis, we can predict how algorithms will perform with when we scale this algorithm with larger inputs. Okay.
Okay.
So here, yeah. So, so when we increase the uh, the number of elements, okay, then as the number of elements increase, the log p also will increase, right?
Yes.
So hence this solution cannot be cost optimal. The theta of n log p cannot be cost optimal, which is not equivalent to theta of n. As number of processes increase, the as and p will also increase. That's why. Okay, is it
Okay.
clear?
Yep.
Okay.
Yep. Yep. As we keep on increasing n log p is
Yeah,
going to be always greater than theta of n.
yes.
Is the
So
idea.
basically,
Okay.
the behavior of a function or algorithm as input size increases and approaches infinity. That's how
Okay.
we talk in terms of asymptotic analysis.
Okay. Okay. Thanks.
Okay. So yes. So the first one is Amdahl's law. So now we know what is speed up. Speed up is the execution time serial divided by parallel execution time, right? But how can we calculate speed up in terms of the time taken for executing some part of the portion of your program serially? So that fraction cannot be parallelized and it will always remain sequential. Okay. Now this portion could be, we can think of it in terms of, let's say we are trying to uh, maybe perform, let's say, summation of elements that we just performed. Each processor is doing the summation. Okay. Now the final processor has to then, let's say, okay, instead of communicating one value, it might have to communicate so same n values. Okay. So the final output is to be given to a IO device. Maybe it has to be shared to a printer, or it has to be shared with a uh, a monitor or any other input output device. In that case, that part of your code will has to be done sequentially, serially. Okay. And maybe it is not possible to parallelize this part. In that case, even if your processing can be done parallelly, that sequential part cannot be avoided, and it will always remain as part of your, as part of your application. And that will ensure that, or it will dominate the parallelism that you can achieve in a program. So how do you calculate speed up if you have a certain section of your code that always that needs to be executed always serially? So this portion is known as F, which is a sequential portion in your code, and this is greater than 0 and less than 1. And if you have F fraction of your code which is executed serially, in that case, the maximum speed up that you can achieve in your code is 1 divided by F plus 1 minus F divided by P. Okay. So with this, you can calculate the speed up that you can get if you have a fraction F in which is always serial in your code. Okay. Since some of you said that you have learnt about Amdahl's law in some other course, what are you aware of? What are the limitations, or what is wrong with the speed up that is calculated using Amdahl's law? Is this
Amdo's
good enough?
laws, yeah, Amdo's laws is considering the workloads are constant, but only changes happening at the processes and all. So, in ideal scenario, real-time scenario, workloads also dynamically changes for sequential and parallel program.
Yes.
Ma'am,
So,
in the MDAS
uh,
law, one more thing is not considered. I believe the communication overhead. The more processor, and we don't know what is the communication overhead will be there in among those processor or processing units, or kind of segregated computers. So at that place, it is. I mean, it's not giving that formulation. So it doesn't consider while building the formula those overheads. It is considering like they are very well connected in one system only. But in
yes,
practical,
correct.
things can be very far off places, right? One computer can be in Mumbai, another computer can be in Kolkata, like that.
Yeah, you're correct. Overhead is not considered. Yes. Any other?
Before that, can you tell that what is the ideal speed up value? What should be the ideal speed up value?
The ideal speed up is expected to be the P, right? The number of processors that you use. Let's say you are using 5 processors instead of one, you expect your speed up to be 5 times better than using one processor, right?
So it's directly proportional to number of P's that we have.
Number of P's that we have is what is expected, which is ideal, which is not what we achieve.
Okay.
But ideally, we expect it P times. So, yeah, so Amdahl's law assumes that the problem size remains constant, and with increasing problem size, there will be no change in the sequential fraction of your code, and this may not be realistic. It also ignores the overhead cost, which is associated with parallelization, such as communication, synchronization, and it also does not account for scalability. That is, what if we increase the parallel systems and add more elements, or make the problem change the problem size to larger? What will be the impact on this speed up? Okay, so we can call Amdahl's law to be overly pessimistic, because it assumes that the serial portion of the code cannot be parallelized and will remain the same in terms of its size. And hence, the Amdahl's law is not accurately able to predict the performance in most scenarios. Okay, and hence we need some more advanced model which can be able to accurately predict this speed up. So
Ma'am,
one
can
such
you?
model is, yeah.
I missed the last two, 3 pointers. Can you just briefly tell about the disadvantages?
Yeah. So the limitations of Amdahl's law. First one, it assumes the problem size remains constant. Okay, which is not realistic. First. Second, it ignores the overhead. Overhead in terms of cost associated with parallelization, which may include communication and synchronization. The third point, it does not account for any scalability. So it does not consider that a parallel system can scale and can get or use larger problem sizes, and with larger problem sizes can affect directly the sequential portion that you have. Also the parallel portion may increase or decrease. Okay, hence Amdahl's law is called overly pessimistic. Okay, because it assumes the serial portion of the code will not change, it will remain as it is, and that's using which we are predicting the speed up. Okay, so now how can we consider the scaling of problem size? And for that, we have the next law, which is the Gustafson's law. So here, what we are doing is we are calculating the time, the speed up, by using the time spent in the sequential component by parallel program, which is T of n comma p. Time spent in parallel part is T of n by p into 1 by f. And any sequential implementation must take the T of n by p f, because sequential component, plus pt into n by p into 1 by f. Hence, the speed up is the sequential implementation, that is T of n by p into f, plus pt of tn comma p into 1 minus f divided by T of n by p, which gives us f plus p of 1 minus f. F is again sequential portion plus the number of processes into 1 minus the sequential fraction. Okay. In Gustafson's law, the F accounts for the overheads of parallel computation. Okay. So, yeah. So basically, this F is the fraction of the program that can be parallelized. That is what we considered here. Okay. And the P is the number of processes. Okay. So Gustafson's law is more optimistic because it is predicting greater potential speed up, and we'll see an example next which will show how this gives the greatest potential for speed up. It also assumes that problem size is k with number of processors, and it calculates the speed up based on the scaled workload. Okay, it can handle larger problems also. So we'll see this example. You can Yeah, you can calculate the speed up using Amdahl's law and Gustavson's law and tell me the what are the values for this particular problem. So this will help you to, yeah, understand the difference between the two. So Gustavson's law is P plus 1 minus P into N, whereas Amdahl's law is 1 divided by 1 minus P plus P divided by N.
Amda's one, it's coming 15.625 something speed up.
Yeah,
Yes,
around 15, and with Gustafson's, it's around 60, 60.
yes. So you saw the difference? 60, right? 60.885 something.
Yeah, 60.85.
85, right? Okay. So did you see the difference in terms of speed up that it computes for and how Amdahl's law considers this increase, the increase in problem size?
Ma'am, can you go back on the earlier page wherein we have those formulas? Yeah.
So yeah.
Here, size of problem in both the formulas is not considered that way, if you see, right?
So what is happening here is
Hmm.
in Gustafson's law, we are saying that this is the serial fraction, right? The serial fraction we are dividing by the number of processes. Okay. Whereas here we are in the Amdahl's law, we are only dividing what is the parallel fraction by number of processes, and we say that serial fraction remains constant.
Correct, but only the portion which can be made parallel is going to be
But
divided,
in
and then it's going to take lesser time, right?
yes, so only the so in Gustafson's law, we are multiplying the non-parallelizable part by the number of processes, right? Whereas in Amdahl's law, we are multiplying the we are dividing the part which is parallelizable by number of processes. Okay. So we are considering that the non-parallelizable portion will remain constant in Amdahl's law. Correct?
Mm-hmm.
So,
Won't
so
won't
yeah,
that be case in both the laws? As in, I'm not able to
mm,
clearly understand why sequential portion size would differ in both the situations. Can you? I think the formula is bit different. On earlier page, it was bit different.
yeah, maybe, yeah. I think
Okay. Mm-hmm.
okay. Let's stick to this. Okay. So
Mm-hmm.
here the the P is the parallelizable part, right?
Okay.
And P minus one is serial. Okay. Serial or non-parallelizable.
Okay. Okay.
Hmm? Okay. Now, so here the Amdahl's law, what we are saying is 1 minus P remains fixed. It is not getting reduced with the number of processes. Only what can improve is the parallelizable part.
Correct.
Okay.
Correct. Hmm.
Whereas here in Gustafson's law, what we are saying is the parallelizable part will be there, but the non-parallelizable part will also get affected with increasing number of processes. Okay.
Mm-hmm. P and N kind of got
Yeah.
If
misinterpreted it
we
that way. Mm.
how it will affect, man, if we increase processor, I mean, the sequential part will still be running in one processor only, right? I mean, we cannot distribute that task to multiple processors. Only the
No,
parallel portion
can
we can distribute across multiple.
I think P should be serial and P 1 minus P should be the parallel.
So
Yeah, something.
So
mm,
so Gustafsson law, see, it's P plus because the processes will be multiplied only with the parallel section, not with the sequential section. So ideally P
then
should be sequential and 1 minus P should be the parallel section.
okay, here the F is the serial section.
Yeah,
1 minus F is the parallel section.
parallel
So
section.
this is 1. This is 1 minus P plus P by N, right? Basically. Okay. So yes, so the parallelizable part is getting divided. This
Right.
remains fixed. Huh? And in Gustafson's law, it is
It's being added by
P,
P along with the
P
P
into
plus.
N
Yeah.
plus 1 minus P, right? So what is wrong you are saying here?
So no, so in earlier slide, what happened is, so if you go to the earlier slide where you have written that P equal to what, my 1 minus P to what. So ideally, it should be reversed. So yeah. If you see the
Oh,
right corner, so P considered as a parallel instead of sequence. It should be sequence, and 1 minus P
oh,
should be
okay.
the parallel. Yeah,
Oh, sorry. This is yeah. This is
yeah,
1
yeah. Yeah.
minus P.
1 minus P,
Okay.
and it should be parallel. It should be parallel and the P should be the sequential. Then we will consider the Gustafsson law like P. So sequential will remain always constant and the
Fixed.
processor will be multiplied with the parallel section.
Okay. Okay. So so here also it will be
And this formula is fine. I
uh,
think this formula is fine. I
huh.
believe the terminology which is mentioned, right? F should be sequential and 1 minus F should be parallel.
Okay. So I will make it consistent across the slides. Okay, it's creating issue because of that.
Now, if you stay on this page now, ma'am,
Yeah,
Yeah, in
yeah.
this
the
also we are doing minus p minus in the Gaussian law. P minus instead of it should be plus, right?
Yeah, it
Yeah,
P
should
it
be
is
plus
P
plus.
plus 1 minus
one
P.
minus
Plus
p,
plus.
one minus p.
Yes.
Uh,
Yeah, this is to be 1 minus p.
yeah, that kind of gave rise to confusion. If you
Yeah, yeah.
get back on earlier page,
Hmm.
okay, now here we say F, which is the serial portion
Hmm.
that will need to be executed in exact same sequence in a way,
Hmm.
plus P
Hmm.
into 1 minus F. 1 minus F is the parallelizable part. So
Hmm.
even with Gustafson's law, we are
Hmm. Hmm.
concentrating on the problem which can be distributed 1 minus F.
Hmm.
And we are considering that if number of processes are increased, then this number would increase effectively, right? But
Yeah.
F remains constant, as in the sequential time is going to be having an impact here as well, right? But just because number of processors are going to increase, the second portion of the sum is going to increase, and that effectively is going to give us a bigger number as against the
Ye-
Amdahl's law. So this becomes more
Yes.
optimistic that way.
Yes. So the term p cross n is expected to increase linearly with n. Okay.
Mhm.
Here in Gustafson's law, whereas in the Amdahl's law, because of the term p by n, as n increases, will approach to zero, right? Mhm. So
Mhm.
that's why it becomes pessimistic. Whereas here, because since it's in the denominator, Amdahl's law becomes pessimistic, whereas Gustafson's law is optimistic because we assume it will increase, the speed up will increase linearly with respect to n. So
Okay.
Amdahl's law
Mhm.
kind of shows diminishing returns as we increase the n, whereas Gustafson's law shows that we'll get near linear speed up as we increase the n.
N is P as in you mean, right? Number
Number
of
of processors. Yeah,
processes
number of
is
processors.
what you're
Yes.
trying to comment. Okay.
Yes. Number of processors. Yes. So yeah, I'll fix the slides and make it uniform. I'll do that and then upload.
Okay. Okay. Thanks.
Okay. So there is a yeah there is a Cartwright metric concept which is used to estimate what is the serial fraction of parallel program when we calculate some experimental speed up results. We can use this to particularly measure the speed up on multiple processors, and if you want to see how much of the program is actually inherently serial. Okay, so uh, where we can use this is in most of the real systems. Speed up is rarely perfect because of all the overheads, communication, and serial parts. So Cartwright metrics can help us to identify whether there is some limit on speed up and whether it is due to algorithmic serial fraction or any overhead. Okay, hence it is more kind of a more practical than just using Amdahl's law, because we use the actual measured speed up here. Okay, so uh, you can note down this formula and then take a look at the next example. Okay, so f is equal to 1 by the speed up
So
achieved minus 1 by p is equal,
so
divided
this
by
is
1 minus 1 by p.
So
Yeah,
curve flat metric, it is targeting to the unparalleled, I mean sequential section, right?
the
So
sequential
how,
function. Yeah, yeah, yeah.
okay, how we can speed up that section?
Okay. How we can calculate that section if that section exists in your code? How did you get? How
Okay,
can you get it?
okay, okay, okay. So
Yeah,
so far in both the laws we have been considering that that section is constant. Now in this part we will be more
calculating
granularly
if it.
checking,
Yeah,
calculating the section.
yeah,
Okay.
yes, yes,
Here P is the number of processor, right?
yeah, yeah. Number of processes
Okay.
and S is the speed.
And this S speed up we are considering from Amdahl's law or Gustafson's laws?
Uh, so it is speed up is serial by parallel.
No, no, that's
Hmm,
fine.
hmm.
But which section, which laws we are section considering? So there are two formulas for speed up now. One from Amdahl's law, one from
No,
the
do
Gustav law.
not. So do not use the law. Use the
Okay.
actual speed up.
So
Serial time
so
by
with
parallel
in
time.
that okay. So in that case, so this S 1/s. So here S refers to what?
It is serial time divided by parallel time.
Serial time divided by okay. So again TS by TP, right?
Yeah, yeah. TS by TP.
Mm, okay.
Okay. So the question is here. So you need to calculate the F in this.
So calculate for just the p value keeping as 8 or for all of the.
So all of them, all of them. P is equal to 2, P is equal to 3, P is equal to 4, 5, 6, 7, 8.
Can you help with one dry run example, as in how to compute it?
Yes. So, yeah. So the formula is F is equal to 1 by S minus 1 by P divided by 1 by P. So F here will be 1 by 1.82 minus, sorry, 1 by P is 1 by 2 divided by 1 minus 1 by 2. Calculate this value for each of these.
It's coming negative for me, so I was a bit confused as in.
Okay. So it is, okay, let me also check. Should not be negative, right? 1/1. Okay, yeah. This should be negative. No, 1 minus 0.54 minus 0.5.
First one is coming 0.09.
Huh. Yeah, 0.09. Even I got 0.09. 0.098.
So, ma'am, we have to convert this into percentage or keep in the fraction?
So, no, that's fine. You can keep the fraction. So basically, you get 0 point, almost 0.1. Is it?
Oh yeah, sorry, there was a mistake from my side.
Yeah. So, so that, so in this, so what can we conclude from this?
Irrespective of how many parallel processes we have, value of f is remaining constant.
Yes, and the reason why with increase in P, the primary reason for pure poor performance is the 10% of competition that is inherently sequential, and parallel overhead is not the reason for the poor speed up. Okay, in this particular problem. This is another example which you can try out later and see if it has similar results, or you have some other observation through this problem. Okay. So yeah, so the references for the performance analysis is from Anand Grama, which is Introduction to Parallel Computing Design Analysis of Algorithm, which is the ebook is easily available. Go through that and learn more about this performance analysis matrix. So with this, we can move to the back to, or I think this is the first, no, which we learned MPI. So this is the second programming model that we are learning today, which is P threads. So we come back to this question of process versus threads. We have seen this before, that process, uh, a single threaded process will have will share code registers, data, counter, files, and stack will remain same. Whereas multi-threaded process will have its own registers, own stack, and counter. Code, data, and files may be shared amongst these different multi-threaded processes, but it will have some portion which is thread specific, some portion which is common to other threads. Now, how do you check number of process threads which are there on your machine? Even if you're using a Windows machine, you can just use a Control Alt Delete and check in the task manager. So there you have to click on more details, performance, and then in CPU you can check the number of cores. So you'll see something like this. So here cores tell you the number of CPUs, and logical processes is the number of threads which are available in your machine. Okay, you can check this out on your own machine, and that's
Ma'am,
how you
this
can check the
logical
process.
threads, is it like core wise or overall how many threads running?
So So these are total threads.
Okay. But there is another threads count. I think it is showing 4184.
So yes, so this so these are different processes that you have. These may not get hold of each, core. Like there might be some concurrent execution happening, may not be parallel execution. So as you know, so the concurrent execution, what happens is you may have multiple threads which are available, and they may execute, use the single core, and the first process thread is current using it, then T2 comes, uses it, then T3 works, then T4, and then again T1 may work. On a single core you are doing this execution. Okay, so parallel execution will mean that each core will have certain number of threads which are working. So in each core, maybe on core 1, T1 and T3 are working. On core 2, only T2, 4, T4 are working.
I mean, in concurrent
So,
execution, um,
yeah.
in concurrent execution, these threads which we see, right, four threads, T1, T2, T3,
Mhm,
T4,
mhm, mhm,
so they'll
mhm.
get the core on a leaf basis. I mean, would it be kind of a round robin sort of a thing, or random? They'll be given access to the core.
Uh, so it depends on the OS which scheduling algorithm it is using. So it it will be decided by the OS how to assign these threads to the codes.
But at a time, only single thread will be running, right, on the core.
Yeah,
It,
yeah. At one time, only single thread will be done.
okay.
So 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 by this it means that we have four physical cores. That is four physical threads. Four physical cores are there, and there are eight logical processes. So there are two per core processors that we can use for running. So totally we can at a time eight threads can be active at a time. So yeah. So now we have seen the distributed computing setup. This is about the thread computing system. So now here what is different is that with MPI we were looking at if the memory is different, if the ports are if the systems are located in different places, how can they communicate through messaging? And the communication used to be explicitly through messaging and not any common variable. Whereas the main difference between distributed and shared memory system is that communication in shared memory happens through memory, that is the shared variables. So let's say in this image, this is S, which is a shared variable, and there are n processes here. Each may have their own private memory, but they also have a shared memory, and they all check the value of S in order to perform some specific operation. Okay, so or they update the value of S so that the other processor can read it and do some task. Okay, so the communication is happening through this shared variable. And what is very important and critical here is how do we synchronize this on in a shared variable so that it does not get altered and the data remains intact. Okay, is it clear? Did you understand the concept of shared memory programming and the difference between distributed and shared memory is clear?
Yes.
Yes,
Mm.
Yes, ma'am.
ma'am. Here,
Yeah.
P0, P1, Pn are used. Those are threads,
Mm.
right? parallel threads
Yes.
of execution. Let's call them out as T0, T1, Tn. As in process and threads are kind of interchangeably used, and that kind of confuses things a bit.
Okay. Okay. Okay.
Here we are
So
just particularly talking about multiple threads within same
threads.
process.
Yes. Yes.
Okay, so let's
Yeah.
call them out
So
as
these are
T.
threads. Okay.
Yeah.
T0, T1. Yeah.
But one more question, ma'am, here, like
Hmm.
thread is like a course only, logical course. So we can treat like a processor also.
Uh, can you repeat?
My question, like we are talking thread. Thread is a logical course that's
Hmm.
equivalent to the processor.
Okay. Huh. Yeah.
Means we are
Which can
saying that,
execute which can execute a particular thread.
yeah, means you just given the example. There are 4 cores, and if there are 2 thread on each course, we are logically saying there are 8 logical processor available to do the processing. That's
Yes.
something we can say like P0 to Pn.
So ideally, what he
Yeah.
means is, physically, if a single core has a two logical cores, where each logical core considered as a thread, so we can
Hmm.
consider that as a processor also, right? So
Yes,
logical processor. So in case we are talking about the thread programming, so at the nutshell, the thread will also be assigned to some logical processor,
Logical
which
process.
which
Yes.
which is again again a kind of processor.
yes,
Yes.
that's
Yes. 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 The logical processes execute the threads.
yes.
Can you just go back on the earlier slide and explain same thing? If you can go back. Yeah. Now here we are seeing, no, the other one, the next one, sorry.
Hmm.
Okay, here what we are trying to say is when we have a single core machine,
Hmm.
we have here 4 threads are there,
Okay.
right? T1, T2, T3, T4.
Yeah.
So
Yeah.
all of them share same single core in a
Hmm.
time slice manner.
Yes.
Here we are not talking about processes,
No.
correct? Now,
Yeah.
same if we have a parallel setup wherein we have 2 cores, then maybe those threads could be divided across those cores. So T1, T3 are kind of assigned to
Hmm.
core 1, while T2,
Hmm.
T4 are
Hmm.
assigned to core 2. And then again, between them, they are going to do time slicing manner, as in core 1 is going to be
Yeah.
used by T1, T3 in a slicing manner. That's what we are
Yes.
saying here. Here we are not
Yes.
talking about processes per se, right? Now, as a matter of fact,
Okay.
let's assume that a process is divided into 4 threads. And let's say T1, T2, T3, T4, all of them correspond to one process which is kind of executed using 4 parallel threads.
Okay.
Can we apply the analogy this way? As in, these threads could be from same process or they could be from different process. It doesn't matter. We are going to deal between core and thread. We are not going to deal between
Yeah.
core and process per se.
Yes. Yes.
Okay,
We yeah, these threads can belong to the same process or may belong to different processes. And now we are looking at them from thread perspective, which are assigned to each core for execution.
right, right. So process is over and above that this slide is the point which I'm trying to make.
No,
So,
but if you think like a
Mhm.
thread is a unit. We are dividing a problem in 4 parts and assigning each thread to one logical course. That's nothing. It's a processor.
No, but we are not assigning thread to core, right? It is operating system's responsibility to do that work. We are just saying that I have a program, I'm dividing it into 4 threads, and each thread is going to do a certain code portion that way.
That's
How it,
that's a
Mhm.
programming portion. We need to
Right.
handle once we do the thread programming, then we need
Mhm.
to partition first our problem and then assign the problem to particular threads based on there
Hmm,
is some
hmm, hmm.
we need to do that in a programming, and OS will take care of that. But here what I am trying to say, thread is nothing, it's a core only.
Yeah, it's a logical processor anyway.
Yes, it's a core only.
Yeah. So within a core, ideally in any physical environment, so within a core, ma'am, correct me. So in
Huh.
single core, there would be a two threads or two logic, which we consider as a two logical cores. Correct. So when we are doing this thread programming, so each thread will be assigned to one of the logical processor.
Yeah. Is there a drop or
Yeah, that.
okay?
Yeah, I mean
Yeah.
that's it. So
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 the OS will OS scheduler will assign the processes or threads to whatever available codes are there depending on whatever scheduling algorithm it has. Okay. So based on the priority or based on uh, what is the load balancing that is needed, it will do the assignment. And then there will be some context switching that can occur between processes or threads between these codes as and how the need arises.
Here I have one question like the cores that
Oh,
we have
yeah.
multi-core. So it
Hmm.
can run thread also or a process also, right? Each
Yes,
core is capable to do the both. I mean, it's just a
yes,
computational unit.
yes. So, so if it is a process which has only single thread, it will have it will share code data files and register counter stack because it is a single thread. But if we divide this single a processor into multiple threads, so if the processor gets divided into multiple threads, it will share the code data and files, and it will have some some local memory also meant to save some other variables such as registers, stacks, and counter. That is the only difference. It can either run as a process or as thread, and based on whether it's a process or thread, it's the memory or the assignment of data to it will differ.
Ma'am, one more question here, right? So we were
Yeah.
talking about distributed computing, right? Where we are saying that we are breaking our entire program into multiple processes, right? And assigning that process maybe to a set of different set of machines, right? And each of them having their own cores. Now, if a process is in a machine which is running on a core, right? Which could be any core of that machine. So thread is part of that process. So ideally, that thread should be running inside that core only, right? Because it's a part of process. It's not like
Process.
so.
Hmm.
How are we? Yeah. So my question is, how are we distributing threads from a single process onto multiple cores? I mean, how is that uh, possible, or how are we doing it? If you go to the slide where you were showing concurrent
Hmm.
that part, where is that? Yeah, this one. Prior to this slide,
Hmm. This
this one,
one.
parallel
Okay.
execution, right? So we are saying that
Hmm.
my process. So first is the entire program, then we have processes, and then we have
Hmm.
threads, right? Now, if I'm saying
Hmm.
that my single process is running on a specific core, obviously my
Hmm.
threads are part of my process. So if my process is on
Hmm.
a core itself, how am I able to divide multiple cores onto multiple threads onto multiple cores? How is that happening?
Okay. Okay. Yeah. So, okay. So first of all, you know, when we are trying to do the assignment of threads to cores, the the scheduler, OS scheduler, will assign based on the availability of cores. Okay. Now comes the factors like there could be priority, load balancing, and or
Ma'am,
cache, like how much is the cache required.
I
So,
think
but yes,
just want to mention. I think so. You got my question right. So what I'm trying to say is, I have a
yeah.
single
So the
program. Mhm.
hmm, 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 hmm.
No, I
Okay,
have a
yeah, yeah.
single
You
program,
repeat,
big
repeat.
program, right? Yeah,
Hmm,
I'll just repeat it again, right? I have a single
yeah, yeah.
program. Inside it, I have multiple processes. Inside the
Hmm,
process, I have multiple threads. That is correct, right?
yeah.
My understanding.
Yes, 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 yes,
So
yes.
prior to today's class, we were saying that we are running multiple processes on multiple systems, which means obviously different cores, right? And if I have a
Yeah.
process one which is running on, let's suppose, core A, I'm just
Hmm,
calling as, or maybe core one, right? I'm just saying that.
hmm,
So
hmm,
obviously,
hmm.
that process, the threads of that process should run on core one only, right? So how am
Not
I saying?
not necessary. Not necessary. When the processor has multiple, when a process has multiple threads, then the system may distribute these threads across what available cores. They may not run on the same. They may run concurrently on multiple cores. That's allowed.
Yes, yes, because core is just a computational unit. So whichever
Yeah.
available OS will delegate to that.
So yeah. So basically, scheduler will balance the workload across different cores, whatever is available,
Okay,
and
yeah,
that's how we can achieve performance.
got it. Yeah.
Then there is no point in dividing a process into multiple threads if the same core is supposed to run the same all the task of one process. Imagine what will happen in that scenario.
So, ma'am, in that way, there is no tight coupling, right? If a process is delegated to core one, it should not be like that.
Hmm.
Its threads also will be running in core one. It may be delegated to some other available cores, right?
Yeah, so if the process, let's say, divided into four threads, then each thread of that process could be running on a different core and then parallelly completing the task. And that's how we can achieve performance. If we say that one process, all four threads of that process will run on the single core itself, then it will basically become sequential competition and it will not help us in gaining any kind of performance.
Yes.
Here,
Ma'am, just to clarify, process
huh.
itself doesn't get executed on core. That's my current understanding. It is thread which correspond to that process. Process could be one single threaded, as in only one thread. So that thread gets scheduled on core and it gets executed. If it is multiple threads, then multiple threads corresponding to that process would get executed on multiple cores. So it is thread which gets linked with core. It is not the
Yes,
process directly, right?
yes, yes.
Okay.
Process, if it is single threaded, then one that
Then we
thread of
can say
that
that,
process,
yeah, process is getting
multi-threaded. Yeah,
allocated. Hmm.
yeah.
Okay.
So
But it
basically,
is thread.
processes rely on thread for
Okay.
execution on
Hmm.
codes.
Okay. I see. Yeah. Thanks.
Okay. So, in child memory programming, as we've seen, it's easy to program, hard to scale because increasing there is a hardware limit on how much shared memory we can have in a multi-core processor system. Okay, it is if it is a single node, it is great, it is useful. We are able to gain good performance. But because it's shared memory, shared variables, we have to balance the parallelism that we can achieve in this code in terms of synchronization that is needed. Okay, the popular APIs are OpenMP, mm, pthreads, and Java threads. We'll learn about or we'll start a bit of pthreads in today's class. May not be able to do much, but uh, followed by once we complete learn pthreads, we will learn about OpenMP. Okay, but starting with understanding pthreads gives you uh, more granularity kind of in terms of how the execution happens in a multi multi-thread system. With OpenMP, it is slightly easier to program, and you do not get the granularity at the level that pthreads provides you. Okay, so we'll see once you uh, see some examples, you will be able to understand it better. So, sorry, yeah. So, pthreads defines how threads should be created, managed, and destroyed, and this library helps you to create and manage the threads. You don't have to worry much about the implementation details; those are taken care of by the library. So we'll see a few functions. The first one is how do you create the thread? In this, the function is pthread underscore create, where you provide a TID, which is a thread ID basically. T attribute is attributes of the thread, usually null, but you can add any attribute if you want for specific thread. The uh, so this you can use this basically the attributes for scheduling for text on text sizes. You can use that. The start routine is the function that you share, which creates the new thread and will execute some part of the code if you want. Argument is the argument that you share with this start routine. So if you want to pass some values to this function, we wrap them in a pointer and share it here in the argument. So once the once this call happens, a new thread is created and it will begin the execution using the start routine. So we'll see that example. So the next one is pthread join. So once you create the thread, then you will start the thread, and once the thread completes the execution, you will once it finishes, the pthread join is used to wait for this thread to finish the execution. So here again you have to provide the ID of the thread that we want to wait for completion, the status, that is a pointer which which will tell the exit status of the thread, and uh, if there is any so the status can be even null if we don't care about what should be the return value of this join function. So when we basically call the pthread join, the calling thread will be blocked until the specific thread finishes, and this will ensure that the thread that is called is completes its work. So
Ma'am,
basically, this is how it
sorry,
looks.
can you go back,
Yeah,
please? Just to clear
yeah,
this concept. Yeah. So
yeah.
pthread create is something we created. Now, once all the threads completing their job, so
Hmm.
the join, is it equal to the MPI gather or something like that, or gather all,
No,
or
no,
it is
Barrier.
a barrier?
It's MPI barrier. It's similar
It's
to that.
MPI similar to
no,
that.
Not
not
exactly,
no.
but similar to that. As in,
Huh.
pthread join will help you to wait until certain else thread is complete.
No, pthread join is basically thread termination. You terminate the thread. You uh, you create a thread from the starting thread, or the one who begins. You create a
Mhm.
thread, and then it will do some task, and it will join. Means it will finish its task and join back the main thread.
Main process means.
Yeah, yeah.
Okay. So and how the result will be going back to the main process from the thread?
So it depends on the problem that we are looking at. So we'll see
Mm.
a few examples. I think that will give you an idea. So
Okay.
so you can see this example. This is a very basic example where this thread is supposed to print a message. Okay, some message. Okay, so we create the pthread. Create thread ID is given. No attributes. The function is print message, and whatever argument you want to share, whatever message you want to share, you send it through this argmin. Okay, that you get through main function. This will create the thread. The thread will print this message. If there is any other task that it needs to do, you have to put it in this function for your message, for your thread. Will complete that. Once it is done, pthread join. When this will execute, the thread that you created will complete its task and finish. It will go back. Okay. So
So, ma'am, is it like
basically,
that? Is it like
basically,
finalized?
yeah. So let me explain through this. So the main function started. Okay, here by thread zero. Okay. Now when it reached after a few instruction, it reaches the create thread function. Okay. Create thread function then starts print message. Print message finishes the problem. Once the print message is done, it will come to join. Okay. Once the join happens, this thread goes back or stops and joins the main thread. And now only main thread will execute.
So you're saying when
Okay.
thread is created, then the message is through thread one. Didn't get this. So we are creating a single thread only at the end, right?
Mhm.
So why this thread one? I didn't get that part.
So no. See, thread zero is the process has started, the main function, the code is started here.
Okay,
Once the
okay.
main function starts creating this function, now this whole thing will be executed by thread zero, T0. Okay. Here you came and created a thread, new thread. This becomes T1. Sorry, my mouse is. This becomes T1. Okay. T1 will execute the print message. Now it will join. So T1 then joins T0 and now return will be executed by T0. Is it clear?
No, but thread
Ma'am,
one will not go away anywhere, right? Because
Huh?
thread one was, if you go
So
back to
you,
the,
yeah.
here we are saying that in join, it is coming back to thread zero, which is executing this program, right?
Mhm.
But thread one is the actual thread which is created through create thread message. I mean, create
Yeah.
thread function.
Yes. So you can have more than one, right? You can have T1, T2, 3T, T3, and so on.
So is it like the MPI finalize where we are saying that we've done the
Yeah.
computation?
But you have a exit function also here.
Okay.
So, so in pthread, all threads exist in with the exit system call. The entire process is terminated. So all threads are killed by OS if you do pthread exit. Okay.
ma'am,
So
are this thread is non-blocking or blocking?
hmm,
Thread, whatever
mm,
the threads we are creating, is this non-blocking?
mm, okay. So you
Oh, blocking
uh,
will happen when we join,
pthread
right?
join becomes a join is a blocking call, right?
Yes.
Because it is waiting for the thread completion. But there are other non-blocking calls that you have. But pthread join is a blocking call.
Ma'am,
Means
this P thread, that library, is it a C++? The library is
Yeah,
there
it's a
to
C
create.
library. Yeah, yeah,
Okay.
yeah.
Okay.
So I'll show a real code example. I think we'll see an example. So okay, so this is a very this is we'll go through this example and rest maybe will in the next. So this is a simple code which we are trying to execute with using multiple threads and using a single thread. Okay. So here basically what we are having is this code visible? So there is a
Yes.
task, do work, and that we have put in a for loop. Okay. In the for loop, we are calling this function multiple times and asking it to do task. Okay. The task is the number of iterations are 10. So 10 times we will call this function. We'll say task starting and it will sleep for some time to just show that it is doing some task and print of task done. Okay. So let's execute this code. Is this code clear?
Yes.
Okay. So single thread GCC and time a dot out. So 10 tasks are done. So the time, the real time is around 5.021 seconds. Let's execute it one more time just to get an average or like have an idea of
And
how
how
much
is it?
time it takes.
Where is the thread being created here? We don't have thread right now currently, right?
No.
It's just a
So this
normal
process is a
programming.
single threaded process. This process is single threaded.
No, even in
No
single
thread
thread,
creation.
no, when you're saying single thread, then also we have to create one thread, right? Through that method, the
So
function
that
that
is
we have.
taken care of by a main function, right? The compiler is been creating for main function. We are not
No, what?
explicitly creating any threads.
No, my question is that in exam, if we get that create a program for a single threaded kind of a thing, right? So in that case, we don't have to create that thread because last in your last PPT where we were seeing thread
Hmm.
0 and thread 1, we had created one thread 1, right? So that was a single thread we created, and then it joined to thread 0, which was executing the program. So wouldn't we write that code itself instead of this code?
Uh, okay. So if you are asked, the question will be much more specific. It will clearly ask you how many, what each that thread needs to be done, how it should be created, where it should be created, what are the tasks. So do not worry, there will be no such confusion.
So
Okay.
in the earlier
Hmm.
example in PPT, that is so that
Ah,
program is for how many threads? That is for one thread only, right?
Two
yeah,
threads.
that
That way,
two
right?
threads basically.
Two
Two
threads.
threads.
See,
No, when
main.
you start the
Hmm.
main
Exactly.
method, right? The main thread starts. So
Correct.
when you run
Hmm.
the code, main thread starts. Always it is
Yeah.
single threaded until you spawn
Ah,
another thread. From
another thread.
then on, the
Yeah.
thread count is you can have the control how many threads you want to spawn.
Yes. Yes.
Yep.
Yes.
Okay.
Yep.
So basically by default main is creating one thread 0.
Yes,
Yes.
like someone pointed out earlier, right? Process itself doesn't run, thread runs. So the process creates
Hmm.
the main thread as soon as it hits the main method. So first thing it will do is run this main method, right? There your
Hmm.
thread has already started. As soon as you run that MPI execute or whatever C program, when you run the code, main thread will start.
Got it. No, that makes sense. Yeah. Thank you.
Yeah, and more importantly, each program will have only one main method.
Yeah,
It cannot
that
have
I understand.
multiple main methods, right? So main becomes the entry point. As soon as process starts, how does OS knows from where I need to start? It looks at the main method, right? So
Even
that's
exit
the,
also.
yeah, even exit also, correct. So when we say return zero, that zero is being written to the operating system. That signifies the thread execution is complete. So here when we say main, it is actually the main thread for the process. And then once we get control over, as in if we spawn threads, then it becomes the other threads, as in thread zero,
Mhm.
zero is constant, 1, 2, 3, 4, 5 are some things which we can kind of spawn and decide what we want to do.
Mhm.
As far as this example is concerned, there is only one thread, one process, one thread. And that thread is invoking that method, do work method.
Yes. Yes.
Yeah.
Hmm. No,
Hope
I
that
get you.
helps. Yeah.
Yeah, yeah. Thank you so much. Yeah.
Mhm. Okay. So now we look at a multi-threaded implementation. Here we are creating 10 threads. So in this function, we are using pthread create and each thread gets created. The attribute is null and it calls a do work function and it provides the ID to be I for that particular function. For execution of the argument that comes is a ID of each thread. Okay. Now we create this function. This will print the task is started and it will complete the task. There will be the same amount of sleep for each task. And then eventually, once the creation is done, the task is done, we join all the threads. Okay, the threads are expected to finish or terminate by joining the main thread. Now, if we run this code, it will be GCC multithread.c, and we have to add minus LP thread. Okay, if you see the difference here is we have added a hash include pthread.each h header file. Because of that, we have to provide this minus or dash LP thread. Okay, this will compile and create a a.out file. So same task done. Okay, if we check the time of this a.out, the time is 0.509 seconds. Okay, and earlier the time was 5.020 seconds. Same task done using 10 threads. We are able to get how much speed up are we seeing here? parallel in 0.5 and
10 times.
almost 10
10 times.
times, which is like almost ideal, right?
Yes.
But not much communication in shared memory. So there also we are not doing any synchronization and communication also. That's the reason we are seeing that almost 10 seconds. But you saw the difference in terms of how just adding the threads helps in terms of performance.
Yes.
Hmm?
Ma'am, this P thread by default comes with GCC, or we need to?
Yeah, with GCC it comes.
Okay.
So that linking is required, that dash LP thread is required. So it will be there in GCC, but linking is must. Without this linking, you will not be able to use. And the bthread.h header file.
So basically, we need to pass this linker option mandatory.
Yeah, linker option. We can just go through a hello world program also, and then maybe the synchronization part we start in the next class. I don't want to leave it halfway. So here, what are we doing? We are creating 4 threads, and each thread will be created by pthread create function, and it will print a message hello world for hello from thread number PID. PID will be sent using T again, which will give it its thread ID, and then we will do pthread join. All the threads will be joined. If all threads have to be finished, and then we will do the exit. So hello world minus LP thread. So we are creating thread hello from each thread. The order may change depending on if there is any delay, but all threads get created and say hello, and then they all finish. So I think we'll stop here, and the synchronization part we will start in the next class. Okay. But yeah, I know there are queries with respect to the lab which are not sorted yet, and somehow they are not responding to my mails or calls. I'm just redirected from one person to another. So what I suggest is you all use your systems, use Visual Studio Code or WSL and try the examples that I share in the eLearn portal. I will most probably not give programming assignments as such, which will be evaluated, but I will provide programming problems as practice problems, which are open to y'all. Whoever is interested can do those and practice and try to solve those problems. I'll try to provide some interesting problems as well. So which I am planning to. So it's up to you if you want to spend some time live with these programming models. You can go ahead and practice those. Okay, but I will most probably not have evaluative assignment problems.
Ma'am,
So evaluation will be based on quizzes and the mid-sem and compre. Yeah.
ma'am, I pasted the module 2 topics mentioned in handouts. So I'm just trying to
Okay.
align what we are studying right now. Which of the section
Okay.
we are covering? I believe.
So this is shared memory is module 3. Right?
Okay, currently we are talking about module 3. So I was thinking, so in
Yeah.
this, the content I pasted from this module 2. So,
Uh,
so module 2, like first topic is the concept of data partitioning, paralleling. So these topic will
uh.
come next or
So
how is it?
we have learned OpenMP. Okay,
Uh-huh.
OpenMP from module 2.
Yes.
We have learned synchronization and tasks from OpenMP perspective,
Uh-huh.
OpenMPI perspective. Sorry. Okay.
Yes.
Uh, so, but we have not done multi-node kind of issues or how do we partition across multiple nodes, which I was hoping we'll get the lab access and we'll do it. But I am so depending on whether I get the access, I'll see if I can cover those. But for now, you learn OpenMPI in this module, whatever
Mhm.
we have covered so far, and understand how we can distribute the uh, distribute the task amongst different processes and how they can communicate through messaging. Okay, and same thing. I think I briefly also mentioned how we can run it on the uh, on the nodes if we get access to, right? There, so the
Okay.
difference is not much. You will not find much difference. You try it on your
Okay.
machine, and because the communication is and this is taken care of by the library, MPI library. You don't have to bother about.
Mhm.
So,
Okay.
so
And when we do
MPI is
actual.
what we learned in module 2. Okay, MPI is what we learned in module 2.
Okay, so primarily it was an OpenMPI bullet number 3 is we are referring
Yes.
3, and
Yeah.
then we covered like uh, where is that? Uh, so I'm just trying to just match what we so bullet number 2 we covered, bullet number 3 we covered, and bullet number 4 covered communication cost we covered, and
Yes.
throttling
Yes.
flow control is something we have not covered because of the lab and all. Is it
We have
right?
not covered. Yeah.
Payload
Yeah.
synchronization problems is also something we are covering
We
going to
have
cover.
covered. We have covered. Yeah, we have covered some, and we will learn about synchronization problems in other models as well. That will be there
Okay,
covered
a
as well.
rest
So
3 is
I'll see
something we have.
how I can cover. Yeah, I'll see how I can cover them in later classes
Okay,
once
so
we have your lab
in
access.
yeah, in practical, when we have a multi-node environment, so just for practically
Mm,
understanding, so first we need
mm,
to create in a code. When let's say
mm,
I want to test it the MPI, the message passing from one node to another node, from one process and one node to another process to the another node. So
mhm,
in that case, I
mhm.
have to write down the socket programming, and then within socket we have to perform the exchange of the data. And
Not
is that
no you for MPI you will not need socket programming in it with respect to MPI. I think I did mention it in third one. Did I? So
mm, this
uh,
So within same system anyway, we are doing when
Message person.
we are creating MPA code, that is anyway two different processes
Yeah,
we are creating, right? So
yeah.
send and receive and kind of thing. But when we have
Yes.
to create the same thing in the multiple, like actual this environment,
So
multi-node
the
environment.
yeah, so the so it will only have what will differ is the
Yeah.
MPI uh, the MPI run file you will have to give the host file name which will tell what are the hosts in your environment. Okay, so what
Okay.
are the different nodes in environment, and this file will be located in some place which you have to mention,
Hmm.
and then the same MPI executable will be executed, and it will
So
take
it
care of dividing the work among different nodes and everything.
okay, it will automatically do. So we don't need to define anything.
Yeah,
So
we don't
so
know that all is taken care of by the programming library, the MPI library.
So this host name, how would we define into the code? So this host name will be like considering as a
File.
process or file.
So it's a file which will have the IP addresses and the host names, the node
So
names.
yeah, I mean, I'm asking, let's say manager considering process rank
Hmm.
0, then worker 1, 2, 3 considering 1, 2, 3 respectively the rank.
Hmm.
So these will be considered. Is that way that we should consider?
Yeah, so manager will be the main main thread which will
Uh-huh.
then assign tasks to maybe worker threads, and
Okay,
then
like
worker threads yeah will have the each node will have a file where it will know who is its manager and what is its IP address
hmm.
for slave nodes.
So in code we have to define them the rank of these each of the node, correct?
Yeah, yeah.
Okay. Okay. Yeah. Thank you.
So yeah, rank will be assigned. Maybe I'll try to do a few examples. If even if without a lab, I will include them in the in next few classes. I'll do that so that you will have better clarity in terms of how that is done.
Sure.
Okay.
Yeah.
So okay, so we can stop here today, and yeah, we'll meet in the next class. Where we will cover the p threads and complete the p threads. I'll see if I want to complete the MPI multi-node that time or start with OpenMP. So either I'll complete the OpenMP and then go back to MPI multi-node, or do the MPI multi-node first and then the OpenMP. I'll see how I feel it is better with the flow. Hmm?
Yeah, ma'am, one more thing. Just kindly share the
Huh.
PPT. Okay.